Hi everyone, welcome to this detailed walkthrough of the OCR A-Level Chemistry Paper 2 of June 2018. This paper contains questions based on synthesis and analytical techniques. It is for 100 marks and is of 2 hours and 15 minutes duration. As usual in this walkthrough also, I shall try not to be slow so that I will respect your time, and also I will not be too fast such that you don't need to pause and rewind several times to understand what's going on. I shall try to write out the methods and answers as we go along in the walkthrough so that it will help you to assess how much time it would actually take in the real exam. Now let's get on with the questions. Question 1. Which compound is used as a standard for NMR chemical shift measurements? It is this compound called tetramethylsilane, or otherwise famously known as TMS. There are a few reasons why TMS is the optimum compound for this. First and foremost, it produces a sharp non-fluctuating peak for carbon as well as for hydrogen environment, even if the concentration of the solution is low. Hence, the chemical shift created by TMS is calibrated as delta is equal to 0 ppm. This helps to compare the peaks created by the other compounds. The reason for the sharp non-fluctuating peaks created by TMS is its shape. It is Si with CH3 in 4 identical positions in symmetry. You can see that these 12 protons are in identical environments. These 4 carbon atoms are also in identical environments. Two other reasons are that TMS has got low boiling point, makes it quite easy to separate it from the sample under investigation, and secondly, it's also very unreactive. It will not bond with the compound under investigation. Now let us look at the other options. CdCl3 and CCl4 both will not produce any peaks in hydrogen environments because they don't have hydrogen, and D2O will not produce peaks in both carbon as well as in hydrogen environments because it doesn't have hydrogen and carbon. Therefore, A is the only solution correct. Question 2. Which compound is a secondary amide? Now, amides are formed from carboxylic acids by the replacement of the hydroxyl group in the acid group by an amino group. So, for example, if this is the carboxylic acid group here, functional group, suppose this OH group is replaced by an NH2 group, that is amino group, then it forms an amide. This is a primary amide. Therefore, to form an amide, it's compulsory that the nitrogen atom should be linked with a carbonyl group. Now, suppose one more hydrogen atom is replaced by an alkyl group, then it becomes a secondary amide because 2 carbon atoms are now linked with the nitrogen atom. And if the other hydrogen atom is also replaced by another alkyl group, then it becomes a tertiary amide. Now let us spend a couple of seconds on what are amines and how are they different from amides. Amines are generated from reactions from ammonia, replacement of hydrogen atoms from the ammonia group. For example, there are 3 hydrogen atoms here, right? If one by one these hydrogen atoms are replaced by alkyl groups, let me write it as R1, R2, or even R3. All the 3 hydrogen atoms replaced means it will become amine, right? What's the main difference between the amines and amides? Amides are generated from acids replacing the hydroxyl group, and there should be a CO, that is the carbonyl group directly attached with the nitrogen atom, and amines are generated from NH3. And another main difference is amines in water will form bases, okay, but amides in water will be neutral. Okay, now let's look for the options A, B, C, D. Which one will fit the bill? Let's see. Mainly, nitrogen should be linked with the carbonyl group. If it is not, you can straight away cross it out. This is not having any carbonyl group attached to nitrogen. No. Third one, nitrogen is attached with the carbonyl group. So this is an amide. Now let's look at whether it is a secondary, primary or tertiary amide. So it has got one carbonyl group here and one alkyl group attached to the nitrogen, and the hydrogen is intact there. That means two carbon atoms are linked with the nitrogen atom. Therefore, it is a secondary amide. That's what we are looking for. So C is the option. Let's look at D also before we go. So here nitrogen atom is linked with the carbonyl group. Therefore, it is an amide. Both the hydrogen atoms have been replaced by the alkyl groups. So it is a tertiary amide. And that's not what we want. Therefore, the answer is C. Question 3. Which compound does not react with nucleophile? Nucleophiles have negative charge and they will be attracted by any compound which can be reduced. If you look at option A, it's an aldehyde, and we know that an aldehyde can be reduced to an alcohol. Option B is CH3CH2. It's an alkene, and an alkene is not electron deficient. It is electron surplus. Therefore, it will not get further reduced by this nucleophile. So this could be our answer. Let's look at C and D as well. C. CH3CH2CO CH3. It's a ketone, and ketone can be reduced to a secondary alcohol. So this will react, this will react. Let's look at D. It is a haloalkane. A haloalkane will also react with nucleophiles. Therefore, this is also out. So we have got B. Question 4. Which structure represents an alicyclic compound? So we should look for a structure which does not have benzene ring in it, but at the same time has a cyclic shape. This has benzene, this has benzene, this does not have benzene. So it could be our structure. This has benzene, and therefore C is our correct answer. Question 5. Which molecule is not planar? Planar means flat in shape. You know, compounds which are having carbon centers with double bonds or triple bonds have a planar shape. Carbon centers with single bonds have a three-dimensional shape. So basically this question is asking for which structure under the options A, B, C and D has got a three-dimensional structure. Ethene has a double bond, so it cannot be our answer. Let's look at this H2CO. H2CO is formaldehyde. It has got a double bond because it has got the aldehyde group, and therefore it's also flat in shape. It cannot be our answer. HCN is hydrogen cyanide. It has got a triple bond and it has got a linear shape, that is 180 degrees. Therefore, it cannot be our answer. So the only option here is B, C2H6. C2H6 is ethane. You can see here C, 3 hydrogen atoms here, and C, 3 hydrogen atoms here. So CH3, CH3. It has got a three-dimensional shape. Therefore, that's our answer. Question 6. What is the number of peaks in the proton NMR spectrum of this compound? This is a dicarboxylic acid, and if we redraw the structure, we can easily identify the unique hydrogen environments. So let's draw it now. Carboxylic acid group there, CH2 here, CHOH here from this one, and then we have CH2 here, and then we have got this carboxylic acid group at this end also. These two hydrogen atoms are identical. This is identical with this. So is it identical with this as well? Okay, this is unique. Therefore, this is 3, and this OH group hydrogen atom is number 4. Therefore, the correct option for us is B. Question 7. Ethanol can be prepared by different reactions. Which reaction has the lowest atom economy? Atom economy is the ratio of atomic mass of the desired product to the sum of the atomic masses of all the products. Therefore, to get highest atom economy, there should not be any side product, and for getting a lowest atom economy, there should be byproducts which have high atomic masses. So to figure out the one with the lowest atom economy here, we should be looking for the products with high atomic masses. For option A, there are 2 moles of ethanol and there are 2 carbon dioxide moles here. So it's not very heavy here, therefore it may not be our option. Second is definitely not our answer because C2H5OH alone as the product is 100% atom economy. It's a no straight away. Then C is a giveaway. If you look at this, hydrogen bromide. Bromine itself has got an atomic mass of 79.9. And if you consider option D, ethanoic acid has got a molecular mass of 60, and therefore in comparison C has got the byproducts which have got the heavier atomic masses. So the right answer is C. Question 8. The breakdown of ozone is catalyzed by NO radicals. Which equation is a propagation step in the mechanism for this process? Let us start from the initiation steps to reconstruct what reactions happen. Firstly, the standard oxygen molecules in the atmosphere are split into free oxygen atoms in presence of UV light. So let's write O2 in the atmosphere splits into free oxygen atoms in presence of UV light. In the second initiation step, the nitrous oxide N2O, which is emitted from the Earth's surface due to agricultural processes, etc., that gets reacted with one of these excited oxygen atoms to form the nitric oxide NO radical, which forms the catalyst in this reaction. So balancing it, it is 2NO. There are 2 propagation steps, one in which the NO radicals formed from the earlier reaction break the ozone molecules into a nitrogen dioxide radical, which is an unstable intermediary, plus O2. In the second propagation step, these NO2 radicals react with oxygen atoms to regenerate the nitric oxide plus oxygen again. So these 2 are initiation steps and these 2 are propagation steps. So to mark the answer, we should be looking for either of these 2 reactions written under A, B, C and D. Let's look at it. The first one, no. Second one, NO plus O2, that's not the case. Third one, N plus O3, that's not the case. Fourth one, NO2 plus O, that is this reaction. So this one, therefore that's our correct option. Question 9. Which compound could have produced the IR spectrum below? So let's look at the peaks and the respective wave numbers given in the chart. In infrared spectroscopy, there are mainly two regions, one below the 1600 mark here, and this is called the fingerprint region. This fingerprint region contains highly complex and overlapping vibrations of molecules, and therefore we usually do not use this for functional group identification. This region is called the functional group region. So let's look at this region above 1600 to look at the peaks and the respective wave numbers. The first peak sharp one that we can see here is 2100, 2200 to something like 2300, and then we have 2800 to 2900 or 3000 here, and from this is a broad one which is 3100 to 3000 3600 or 3700. So let's document them here. So 2200 to 2300, the first peak, and the second one 2850 sort of to 3000, and the last one from 3200 to around 3600 or 3700. So let's look into the OCR data sheet, which will be given in your exam. So looking at the wave numbers, so 2200, it is nitriles here, and the next one is 2850, contains alkyl groups, and the last one we had 3200 to 3600, that falls in this region, that is alcohols. So these indicate nitriles, this indicates alkyl group, and this indicates alcohols / phenol. A is CH3CH2OH, so it contains the alcohol group, but it doesn't have the nitrile group, which is prominently indicated by this wave number here, so A cannot be correct. Second one is CH3CHOHCN, so it has got the nitrile group here, and then this is also having OH group here, so this might foot our bill, so let's mark it shortlist here. And the next one CH3COOH, so this is a carboxylic acid group, and if we look into the data sheet, you can see that carboxylic acid should have 2500 to 3300, which is not indicated here, and therefore this cannot be true. Finally, CH3CONH2, so this CO group is not indicated again in our wave number, and therefore B should be the correct option. It contains alcohol group as well as the nitrile group, which are the prominent groups here along with the alkyl groups. Question 10. Benzene reacts with an organic reagent in the presence of a halogen carrier to form phenylethanone. Which organic reagent is required? You can see that this is an electrophilic substitution reaction where the hydrogen atom from the benzene ring is replaced by the ketone group. Benzene has a very stable structure, and it can only react with a species that has a strong carbocation, that is with a strong positive charge. Looking into the options here, only an acyl chloride will be able to do the reaction, that too in presence of aluminum chloride. Aluminum chloride helps by creating a strong electrophile when reacting with ethanoyl chloride. The reaction goes like this: CH3COCl with aluminum chloride forms CH3CO positive plus AlCl4 negative. This is a very strong positive charge which can create a strong enough electrophile to react with the stable benzene ring. The other reagents mentioned in A, B and D will not be enough to synthesize phenylethanone from benzene ring. Ethyl alcohol will not suit because it doesn't have the carbonyl group. Ethanaldehyde and ethanoic acid will not react with benzene under standard conditions, and therefore C is our correct answer. Question 11. How many straight chain structural isomers of C7H15Cl contain a chiral carbon atom? In order to answer this question, firstly let us write the structure of a straight chain heptane. So CH3, CH2, 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 1, 2, 3, 4, 5, 6, CH3 here. Now let us try linking the chlorine atom to the first carbon atom and see what happens. So here it becomes CH2. Now this carbon atom cannot be a chiral carbon atom because it has got two hydrogen atoms linked with it, and similarly all other carbon atoms have got either two hydrogen atoms or a three hydrogen atom linked with them. Therefore none of them is a chiral group. Now let us attach the chlorine atom to the second carbon atom here and remove it from the first one. Therefore, this will become CH3 and this will become CH. Okay. Now looking at this carbon atom, it is linked with one hydrogen atom, one chlorine atom, one methyl group and one pentyl group. Therefore, it is a chiral group, chiral center. So let me put an asterisk there. Okay. In case chlorine is attached here, it's a chiral group. Now let's try and attach chlorine atom here to the third carbon atom and see what happens. So here this is CH2 and this is CH1. And now looking at this carbon atom also, it's similar. It has got only one hydrogen atom, one chlorine atom, one ethyl group and one butyl group attached, and therefore this is also a chiral group, chiral center. Now let us attach the chlorine atom to the fourth one and see what happens. So this becomes CH, this becomes CH2. Okay, now one hydrogen atom, one chlorine atom, but on either side it is attached to similar alkyl groups, and therefore it is not a chiral carbon atom. Now going to the next one, the fifth carbon atom, sixth and seventh, they will all create the similar situations that we have already seen here. Therefore, altogether, to answer this question, there will be only two chiral carbon structural isomers. Therefore, B is our answer. Question 12. The mass spectrum of CH3 twice CH2OH is shown below. Which ion is responsible for the peak with the greatest relative intensity? Okay, this question is quite simple. What we need to do is identify the tallest peak here, look for its MZ value, and look at the options to see which of the ions has got an MR equal to that MZ value. That's it. So the tallest peak here has got an MZ value of 43. Now let's look for the options which have got an MR equal to 43. So this is CH2OH 12, 13, 25, 27, 44. Okay, so it cannot be. Then this one is 15 plus 14 is 29, 39, 41 plus 1 is 42. That also can't be. CH3 twice means 15 times 2, 30. Then 42 plus 1, 43. 43 is there, so it could be. The next one is CH3 15. 15 plus 12, 27. 27 plus 16 is also 43. So we have got two competitors here, this and this. So which one is the right one? Let's see. Now we need to see whether this can be a valid fragment from the compound that we have been analyzing. So CH3 twice CH. CH3 twice CH is a fragmentation that's possible. That ion is possible. So that is still okay. CH3CO positive. CH3CO positive, no way that can have a fragmentation like that. Therefore, C is our correct answer. Question 13. Which statements support or supports the delocalized model for the structure of benzene? Now, three statements are given there. We will review each statement. So, but before going there, let's look at this. Before the current delocalized model of benzene, we had the CAIIB structure for benzene, which had 3 double bonds and single bonds alternating with each other. Now we believe that the structure is a delocalized model with a perfect circle inside here. Now let's read these statements. All carbon-carbon bonds have the same length. Okay, so CAIIB structure had this double bond and single bond, and therefore it was believed that they will be having different lengths of bonds. But actually, when we looked at benzene, scientists came to know that they all had the same length. All the bonds have the same bond length. Therefore, this observation is correct and this supports the delocalized model. Second, the enthalpy change of hydrogenation of benzene is less exothermic than expected. When cyclohexene, a compound similar to benzene but having just one double bond, was hydrogenated, it was found to release 120 kJ per mole. That means the enthalpy of hydrogenation for cyclohexene was minus 120 kJ per mole. Therefore, it was calculated that if benzene had 3 double bonds, then the enthalpy of hydrogenation for benzene should be minus 360 kJ per mole. But the actual experiments showed that the enthalpy of hydrogenation of benzene was only minus 208 kJ per mole. That is less exothermic than it was expected, which actually indicates that the bonds in benzene are more stable than they were expected. Therefore, statement number 2 is also correct. Statement 3. Bromine reacts with benzene less readily than with cyclohexene. That is also true. Benzene, which is actually a test for double bonds, reacts with benzene less readily than with other double bonds. Therefore, this statement is also correct. So, all these go to support the delocalized model. So, let's look at A, B, C, D here. A, 1, 2 and 3. That's correct. So, A. Question 14. A solid organic compound can be purified by recrystallization. Which statements about recrystallization are true? Let's read the statements. 1. The organic compound is more soluble in hot solvent. 2. The hot solution is cooled before the purified organic compound is collected. 3rd, the melting point of the purified organic compound is lower than the impure compound. The first 2 statements are true. The whole idea of recrystallization is dissolve as much of the compound as possible in hot solvent and then retrieve the pure compound by cooling the solution. But the 3rd statement is not true. Impurities disrupt the orderly arrangement of molecules in a solid compound, and this makes it easy to break the intermolecular forces to melt it. Hence, the MP of the purified organic compound is higher than that of the impure compound. But watch out, the boiling point of an impure compound, if the impurity is not volatile, will be higher than the boiling point of the pure compound. Therefore, only statements 1 and 2 are correct here, and therefore the correct option is B. Question 15. Which of the following could react with the compound below to form a carbon-carbon bond? Let us look at the various functional groups in the given compound. There is the phenyl group here, then we have the carbon-bromine bond, and then we have got the carboxylic acid group. The phenyl group, as we discussed in an earlier question, is susceptible to electrophilic attack if it is from a strong positive charge, such as chloroalkane in presence of aluminum chloride. Therefore, the first option will form a CC bond with the phenyl group, as it can attach the methyl group to the benzene ring. So this is correct. The carbon-bromine bond in the given compound is susceptible for a nucleophilic substitution from potassium cyanide, thereby attaching the nitrile group to the carbon atom here, thereby forming the carbon-carbon bond. So this is also correct. The carboxylic acid group will react with the methanol in presence of H2SO4 to produce an ester, but the ester will not create a carbon-carbon bond. Therefore, this is not true. So only 1 and 2 statements are correct. Therefore, correct option is B. We are on to section B now. This question is about reactions of organic compounds containing carbon, hydrogen and oxygen. A chemist investigates 2 reactions of alcohol A as shown below. What is the systematic name of alcohol A? The longest chain is 4 carbon atoms, and therefore it is a derivative of butane. Then on the second carbon atom, the main alcoholic group is attached, therefore it should be butane-2-ol. So let's write the last part of the name, butane-2-ol. Then counting from the right hand side, from nearer the main functional group, on the third carbon atom a methyl group is attached. Therefore it should be 3-methyl butane-2-ol. Part 2. What is the structural formula of alcohol A? So we have 2 methyl groups here, then CH, then CHOH, and CH3. So you could write CH3 twice CH, CHOH, CH3. Part 3. The chemist heats alcohol A with an acid catalyst to form a mixture containing two alkenes. Draw the structures of the two alkenes formed in this reaction. Heating the alcohol with an acid catalyst will result in an elimination reaction where one molecule of water will leave the alcohol. Then the resulting double bond of the alkene will be placed at either of the two places based on which hydrogen atom leaves along with the hydroxy group. It will be clear if we draw the structure here. It was 3-methyl-butane-2-ol, right? Okay, so here the OH group is there. Here the CH3 group is there. The CH3 group is here. There is one hydrogen atom here. There is one hydrogen here as well. And then this has got 3 hydrogen atoms. So when heated with the acid catalyst, this hydroxy group can join with either this hydrogen atom and form a double bond here, or it can join with this hydrogen atom and can form a double bond here. So the question wants us to draw both the structures of the alkenes formed in this reaction. So let us draw the skeletal structure. That's enough for this question. So we have got, there is no OH group now, it's gone, and this methyl group will be there, and the first one will be having a double bond here, and in the second case it will be methyl group again here, but the double bond will be here. That's it. We can also show the structural formula here. CH3 twice, C double bond CH, CH3, and CH3 twice, CH, C double bond CH2. Part 4. The chemist heats alcohol A with sodium chloride and sulfuric acid. Construct a balanced equation for this reaction. Show structures for the organic compounds in your equation. In the reaction of sulfuric acid with alcohol, a proton from the sulfuric acid will join with the OH group from the alcohol and eliminate a water molecule. Then the chlorine from sodium chloride will join with the positively charged species and form a haloalkane. So let us write the equation with the structure here. 3-methyl-butane-2-ol plus NaCl plus H2SO4 will give us the Cl group coming here, taking the position of OH, and then we have NaHSO4 plus H2O to balance the equation. Part B. Compound B, shown below, is reflexed with excess acidified potassium dichromate to form a single organic product. Complete the equation for this reaction. The key operative phrases in this question are reflexed and excess acidified potassium dichromate. Looking at the functional groups in this compound, this part is a primary alcohol because this carbon is attached to just one another carbon atom, and this carbon is attached to 2 other carbon atoms, and therefore this is a secondary alcohol, and this carbon atom is attached to 3 other carbon atoms, therefore it is a tertiary alcohol. So this is quite easy to write this equation if you just remember what happens to the 3 types of alcohols if they are oxidized. The primary alcohol is oxidized all the way to carboxylic acid if it is under reflex, and the secondary alcohol gets oxidized to ketone, and the third tertiary alcohol does not get oxidized at all. So writing this out, CH3, see, nothing happens to this part of the compound. Here this will be oxidized to a ketone because that's a secondary alcoholic group, and then when we come to the primary alcoholic group, we need to convert this into the carboxylic acid group. Between the primary and the secondary alcohols, 2 water molecules are eliminated. Therefore, we should write here 2H2O to balance the equation. So to balance the oxygen, we can see that this oxygen and the 2 oxygens from the water molecules have come in additionally. Therefore, we need to write 3 here to fully balance the equation. Part C. The flowchart below shows some reactions of compound C. In the boxes, draw the organic products of these reactions. Here, compound C is a dicarboxylic acid and it is reacting with excess alcohol and sulfuric acid. Therefore, it will form ester groups on both sides. So we can draw COO CH3 here and COO CH3 here too. In the second part of the reaction with steam and H3PO4, the alkene part in compound C will undergo electrophilic adhesion to form alcohol. So the double bond will not be there now. There will be the OH group here, COOH, COOH here too. So for polymerization, this can only undergo addition polymerization by opening of this double bond because there is no alcohol or amide group to form a polyester or polyamide or anything. Therefore, we just need to write this as a repeat unit of the polymer by opening out this double bond. So addition polymerization. So how do we write that? Draw one COOH here and then put as a single bond. Draw the second COOH here and then draw the hydrogen here and the hydrogen here and then put it up like this. Question 17. The general formula of an alpha amino acid is RCHNH2COOH. The alpha amino acid cysteine, where R is CH2SH, shows optical isomerism. Draw 3D diagrams to show the optical isomers of cysteine. So the chiral carbon atom is this one here, which is attached to this R group, hydrogen, NH2 as well as COOH. So put the chiral carbon atom at the center and draw the R group here. We will fill it up later. And then we have got COOH on one side and we have got the NH2 group on this side and we have got this hydrogen atom here. Now change this into a wedge and change this into a dash. Okay, and let's remove this R and replace it with CH2SH. Okay, now we have this mirror here. So let us draw the exact mirror image here now. CH2, SH and hydrogen are easy to draw. And this one will be the NH2 group here. And this will be the COOH. Let us darken these wedges also. Okay, next question. Part B. The alpha amino acid lysine, where R is CH2 4 times NH2, reacts with an excess of dilute hydrochloric acid to form a salt. Draw the structure of the salt formed in this reaction. Firstly, let us draw the structure of the amino acid lysine. A 2D diagram will do because we are not showing the optical isomerism here. So starting with the central carbon atom, we have got NH2 here. We have got C double bond O, OH here, the carboxylic acid group. We have got the hydrogen here. We have got 4 CH2 groups with the NH2 here. Okay. When dilute hydrochloric acid, and that to excess dilute hydrochloric acid, is reacting with it, it's going to react with the base groups in this compound to form the salt. Therefore, both the NH2 groups will be taking one proton from the hydrochloric acid to form NH3 here. So NH3 positive and NH3 positive here. And since it is a salt, we should also draw the chloride ion side by side. Part C. Alpha amino acids can react to form proteins. A short section of a protein chain is shown below. What is the question? A student hydrolyzes the protein with hot NaOH aqueous. Draw the structures of the organic products formed from this section of the protein. Okay, so hydrolysis actually means that the amino acid is broken down to regenerate the original constituent monomers. You can see from the diagram here that the COOH and NH2 groups had combined to form the amide link here. And on hydrolysis, the COOH will be formed once again, and the amide part will now become the amino group, i.e. the NH2 group. As the amide link breaks here, we will have COOH here and we will have the NH2 here as well. Otherwise, there is no other change in this section. So let's draw that one. So drawing the first part here, CH, CH2, OH, and here we got the NH2 regenerated and we have got the COOH here generated here. Okay, now since the reaction is taking place in an alkaline medium, the hydrolysis will not stop at the formation of the COOH group. It will continue further to form a salt with the sodium hydroxide. Therefore, here it will become a salt and with the Na positive drawn next to it completes the diagram. Likewise, let us draw the second part of the hydrolysis. So here again, the COOH group will be restored. Here again, another COOH group is there, that also will be restored. Here the NH2 group will be restored. This carboxylic acid, both these acid groups will not stop there, they will form sodium salt like in the previous case. Drawing the second part of the hydrolysis group, CH, NH2 here, C double bond O, OH, we will change that to salt a little later, and then here we have got CH2, CH2, C double bond O, and then here OH. Now, as discussed earlier, this carboxylic acid will not stop at here. It will become a carboxylate ion with sodium positive written next to it, completes it. Here as well, negative and then Na positive here, and Na positive in this also. That's it. Question 18. This question is about aromatic compounds. Phenol undergoes nitration more readily than benzene. A student carries out the nitration of phenol with dilute nitric acid to produce 2-nitrophenol and 4-nitrophenol. A small amount of 3-nitrophenol is also produced. The student thought that carbon-13 NMR spectroscopy could be used to distinguish between these 3 nitrophenols. Explain whether the student is correct. Carbon-13 NMR spectroscopy is all about identifying unique carbon environments, right? If you look at the 3 products here, you can't have a line of symmetry for the 2-nitrophenol as well as the 3-nitrophenol, and therefore they both will have 6 unique carbon environments. Hence they will show 6 peaks. But in the case of 4-nitrophenol, you can have this line of symmetry. Therefore, you will have 1 unique carbon here, 2 and 2 here, 3 and 3 here, and the 4th one here. Therefore, 4-nitrophenol will show 4 peaks in the carbon-13 NMR spectroscopy. Hence, we should document here that the student is not correct. We'll explain the reason here. The 2-nitrophenol and 3-nitrophenol will both show 6 carbon peaks, and hence they can't be distinguished. but the 4-nitrophenol will show 4 peaks, and hence it can be distinguished from the others. Right. Part 2. Explain why phenol is nitrated more readily than benzene. The nitration of benzene as well as phenol is an example of electrophilic substitution reaction where the nitronium ion NO2 positive acts as an electrophile. In an earlier question, we discussed that benzene is very stable and it can only react with a strong electrophile with a strong positive charge on it, such as when acyl chloride or a haloalkane reacts with benzene in presence of aluminum chloride. Alternatively, think about benzene ring itself becoming more susceptible to the electrophilic attack by making the ring more electron dense. That's what happens when we talk about the phenol. In phenol, the OH group here has got the oxygen atom which has got a pair of lone electrons, and this partially delocalizes into the benzene ring, making it more electron dense, and hence it becomes more attractive for the nitronium ion to attack the benzene ring. That's the reason why phenol is nitrated more readily than benzene. So let's document the answer here. In phenol, the lone pair of electrons on the oxygen gets partially delocalized. This is the operative word. Into the benzene ring, making it more susceptible to the electrophilic attack. Hence, phenol is nitrated more readily than benzene. Part B. Methylbenzene reacts with sulfur trioxide SO3 to form D shown below. The electrophile in this reaction is SO3. Complete the mechanism for the formation of D. Show curly arrows and the structure of the intermediate. Sulfur trioxide is an exceptionally strong electrophile. These highly electronegative oxygen atoms, 3 in number, pull away the electron density from the sulfur atom, thereby causing a delta positive charge on it. At the same time, the methyl group in methylbenzene, which is otherwise called toluene, pushes the electrons inside the benzene ring and thereby increases the electron density there. But we don't need to draw the curly arrow there because that's only a structural phenomenon by which methyl group activates the benzene ring inside. So what happens here is when sulfur trioxide molecule is nearby, the benzene ring here breaks and the pi electrons actually try to attack the electrophilic sulfur atom in sulfur trioxide. And then at the same time, the double bond here breaks and the electrons here move to the oxygen atom, causing a full negative charge in the oxygen. And this is the intermediate that we need to draw here. So drawing the benzene ring first. Inside we cannot draw the full circle because it is broken, and we need to also show a positive charge here. The methyl group still exists there, and then the sulfur trioxide gets attached here. The two double bonded oxygen atoms are still there, but this oxygen atom is now having only a single bond but with a negative charge on it. Let us also show the CH bond here. Now what happens is this bond breaks and the electrons from here move inside the electron deficient pi ring, thereby restoring the pi ring for the benzene. Now this releases the hydrogen with a positive charge, that is the proton. That's what is shown in the equation as releasing the proton here. This question is about the hydrolysis of haloalkanes. The rate of hydrolysis of a haloalkane depends on the halogen present. State and explain how the halogen in a haloalkane affects the rate of hydrolysis. Hydrolysis of haloalkanes means breaking of the carbon halogen bond and forming an alcohol. And it is common knowledge for us that carbon fluorine bond is the strongest. The next stronger is carbon chlorine. Then the next one is carbon bromine. And the last one is carbon iodine, which is the weakest. Hence, breaking of a carbon fluorine bond will take more time. Hence, we can write that the weaker the halogen carbon bond, the faster will be the hydrolysis reaction. So let's write the weaker the halogen or the carbon halogen bond, is, the faster will be the hydrolysis reaction. Hence, as carbon fluorine bond is the strongest, bond, CF will be hydrolyzed the slowest. The carbon iodine bond is the weakest, and its rate of hydrolysis will be the fastest. You can also mention the carbon bromine and carbon chlorine bonds. So you can say carbon bromine is hydrolyzed faster than carbon chlorine for the same reason. As CCl is stronger than CBr. B. Chlorocyclohexane is hydrolyzed with aqueous sodium hydroxide. Outline the mechanism for this reaction. Show curly arrows, relevant dipoles and the products. Firstly, the electronegativity difference between chlorine and carbon is significant. Therefore, the bonded electrons from this bond will tend to shift towards the chlorine atom, thereby creating a delta negative, and there is a delta positive dipole charges here. The carbon atom with the delta positive charge here is now susceptible for nucleophilic substitution reactions. In the hydrolysis with sodium hydroxide, what happens is this chloride ion is swapped by the hydroxide ion, forming an alcohol. So in NaOH, the ion present is OH minus with the oxygen having a lone pair, which it happily donates to this carbon atom and creates a bond there. And hence this bond breaks and this chloride ion is left free. So we can draw this bond formation as well as the breaking of the bond in this way. OH here plus a chloride ion. Part C. A student hydrolyzes a haloalkane E using the following method. 0.0100 of haloalkane E is refluxed with excess sodium hydroxide aqueous to form a reaction mixture containing an organic compound, product F. The reaction mixture is neutralized with dilute nitric acid. Excess silver nitrate aqueous is added to the reaction mixture. 1.88 G of a precipitate G forms. Organic product F has a molar mass 74.0 grams per mole and has a chiral carbon atom. Question 1. Draw a labeled diagram to show how the student would carry out the hydrolysis of haloalkane E. Refluxed means the mixture is heated and there also should be a condenser at the top. So let us draw a round bottomed flask with a bung or a stopper and a condenser arrangement. Next, let us draw the condenser arrangement. So there is this tube going in and this tube going in. Okay, let's say that's for adding the liquid mixture, and we should have a funnel here to add liquids. Okay, and then we should have a Liebig's condenser here with inlet as well as outlet. Remember, the outlet should always be at the top. And then the cold water in. Alright, and therefore this is called the condenser now. This is the round bottomed flask. It can be a pear shaped bottle also, but don't draw a conical flask because we need to have a heating arrangement at the bottom. Round bottom flask, cold water in. What else is there? We need to have the mixture here and then heating arrangement. It can be a Bunsen burner or any other kind of Bunsen burner. So we can say a heat source. Analyze the information to identify E, F and G. Show your working. So let's write out the equations for the hydrolysis as well as the subsequent reaction as given in the question. So there is this haloalkane reacting with sodium hydroxide aqueous under reflux conditions to form a compound F, and then F is treated with dilute nitric acid to neutralize the excess NaOH in the mixture, and then it is treated with AgNO3 and it forms a compound G, which is a precipitate. What else do we know? Haloalkane is classified as E, and sodium hydroxide F and G. So what else do we do? Now we know that haloalkane is 0.01 moles, and sodium hydroxide, we know its MR is equal to 40 grams per mole, and F is said to contain 1 chiral carbon atom. Okay, and it has got MR is equal to 74 G per mole, and G is said to have a mass of 1.88 grams. Now in this hydrolysis reaction, an alcohol and a halide ion will be formed. That halide ion reacts with silver nitrate to form G. Therefore, G must be a silver halide. Therefore, G is a silver halide. Okay, now it must be having 0.01 moles, because as per the reaction, it's 1-to-1 relationship there. Hence, its MR will be equal to its mass 1.88 grams divided by 0.01 moles is equal to 188 G per mole. Now we know the AR of silver is 107.9 from the data sheet. Therefore, the relative atomic mass of the halide will be, halide AR will be equal to 188 take away 107.9, which is 80.1, which is approximately equal to that of bromine. Therefore, G is AgBr. So box it. That's one part of the question answered. F is an alcohol, and it has got MR given to be equal to 74. Therefore, the MR of the alkyl group will be is equal to 74 minus 16 minus 1, and that's equal to 57. Since the alkane formula is CnH2n plus 2, the alkyl group will be CnH2n plus 1. So that is equal to 57. So calculating from this, 12n plus 2n plus 1 is equal to 57, which gives 14n is equal to 57 minus 156. So n is equal to 4. Therefore, compound F is C4H9OH, and box this also. So let us take this space here. So F is C4H9OH. Okay. Let us draw that. Carbon, 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 carbon. We have been told that it has got a chiral carbon atom. So this is the butane alkane. Now in this, if I put OH anywhere, it should be a chiral carbon atom. So it cannot be in the first and the last, because they are all attached with other hydrogen atoms. In the second one, if you attach this OH group here, this will become a chiral carbon atom. So F is compound butane 2-ol. Okay. Now we have got one more compound to be identified. So that is E. That is the starting haloalkane. That is easy to be identified from here. It will have the same structure as butane 2-ol, where the OH will be having bromine there. So C, H, H, CH2, CH. Remember to place it at the same place where we had the OH. Okay. And then we write the name as is 2-bromobutane and box that also. That's it. End of story. Question 20. Cinnamaldehyde and methyl cinnamaldehyde are naturally occurring organic compounds. Methyl cinnamaldehyde is an E stereoisomer. Explain this statement in terms of the can in gold prelogue rules. As per the CAIIB rules, an E isomer is defined as the one in which the high priority groups are arranged on diagonal sides of the carbon-carbon double bond. If the high priority groups are on the same side of the double bond, then it's called the Z isomer. To demonstrate it diagrammatically, suppose this is the C double bond and you've got A here, B here, C here and D here, 4 different groups. Imagine that D and B happen to be the high priority groups. They are diagonally attached across the double bond. Therefore, it will be an E isomer. But suppose A and B happen to be the high priority groups, and then it will be the Z isomer. By the way, the priority groups are as per the proton number, that is atomic number, and not as per the atomic mass, which is a common student misconception. In methyl cinnamaldehyde, here is the alkene bond. So this is a carbon here. Let me stick this hydrogen also here. Okay, so it has got 4 groups across the double bond. If you look closely, you will see this C6H5 and CHO groups are the high proton number groups, because this is CH3 here. It has got 6 plus 3 only 9 total atomic number, whereas this is 6 plus 1 7 plus 8 15, and C6H5 of course has got more atomic number than these. Hence C6H5 as well as CHO are arranged across diagonally, whereas CH3 and H are arranged on the other side. This is what we have to bring out in our answer. In methyl cinnamaldehyde, the highest priority groups i.e. C6H5 and CHO are arranged diagonally across the carbon double bond. Hence it is there you go. Part B. A student plans to carry out some chemical tests on both cinnamaldehyde and methyl cinnamaldehyde. Question. Suggest a suitable chemical test to confirm that both compounds contain an unsaturated carbon chain. Your answer should include the reagent and observations. The most common test for unsaturation / alkene group is the bromine water test. So write add bromine water separately to each compound and shake. The solution will turn from orange brown, which is the bromine color, to colorless, confirming that both compounds contain an unsaturated carbon chain. Part 2. Describe a chemical test to confirm that both compounds contain an aldehyde functional group. Your answers should include the reagent and observations. The test for an aldehyde functional group is adding Tollens reagent. Tollens reagent contains a silver ion. This reagent will oxidize the CHO group to COOH group while the silver ion gets reduced to silver. That silver will appear as a silver mirror inside the test tube. So add Tollens reagent separately to both compounds. A silver mirror will appear on the sides of the inner sides of the test tube, confirming the presence of aldehyde group. Those who have done this test in the lab will never forget in life. It's a very beautiful silver mirror inside the test tube. Part 3. Describe a chemical test to confirm that cinnamaldehyde and methyl cinnamaldehyde contain a carbonyl group. How could the products of this test be used to distinguish between the two compounds? Your answer should not include spectroscopy. So our answer should be structured in 2 steps. The first step to confirm the presence of the carbonyl group, and the second one how to distinguish between the two compounds. The test is adding 2,4-dinitrophenylhydrazine, or commonly known as DNP. It will produce an orange precipitate. So let's write 1 add 2,4-DNP. It will produce an orange precipitate indicating the presence of the carbonyl group. How to distinguish between the two compounds? So determine the melting point Don't write boiling point. Melting point is a common test. Determine the melting point of the precipitate by comparing the melting point with the known values. We can distinguish the two compounds. That's it. Part C. The flowchart below shows some reactions starting with cinnamaldehyde. Draw the structures of the missing organic compounds in the boxes and add the missing reagents on the dotted line. So this question is testing your knowledge about organic synthesis. So starting from cinnamaldehyde, we can see that a nitrile group is added here and this has become a hydroxy group. In order to add the nitrile group, we need cyanide. So sodium cyanide in presence of acid will synthesize this into this nitrile and the hydroxy groups. Now let's look at this next reaction. When excess hydrogen is added to this compound in presence of nickel, it is a classic case of hydrogenation. You are going to break this alkene bond here by hydrogenating it. And what will happen to the CN? The operative word here is excess hydrogen in presence of nickel. Therefore, the nitrile group will get converted into amino group. Nothing will happen to the OH group here. Alkene group will break as we discussed earlier. And then nothing will happen to the benzene ring because it's quite stable. So we can now draw the structure as okay. So this double bond has been converted into single bond. OH group is still there, and the nitrile group will now become reduce it to CH2 NH2. Now let us look at the next reaction. When you add aqueous H positive to a nitrile compound, it will undergo hydrolysis to form a carboxylic acid as well as an ammonium salt. So let's convert this CN into a COOH group. So just as a note, it undergoes acid hydrolysis CN becomes COOH. Therefore, nothing happens to this double bond because we are just adding H positive here, and then OH also remains as such, but the CN now will become C double bond O OH, the carboxylic acid group. So here, just for your notes, the CN group gets reduced to amine group, and then what happens is the alkene group gets hydrogenated. We are not expected to write these notes here, just for your information only. Let us pick up the next reaction. Cinnamaldehyde is treated with NaBH4. So this is a classic reduction reaction. You know that when an alcohol, a primary alcohol at that, is oxidized, it becomes aldehyde. And therefore, when an aldehyde is reduced, it will become an alcohol. Drawing the structure here, the aldehyde gets reduced to a primary alcohol. So this double bond remains here. This aldehyde group has now converted into primary alcohol. So we can write here gets, as a note only for us, okay, reduce it to a primary alcohol. Part D. Methyl cinemaldehyde reacts with iodine monochloride ICl by electrophilic addition. The reaction produces a mixture containing two different organic products. The electronegativity values of chlorine and iodine are given in the table below. You know, the Pauling scale gives the intensity of electronegativity. Outline the mechanism using the curly arrow model for the formation of one of the organic products and explain which of the two possible organic products is more likely to be formed. In your mechanism, you can show the phenyl group as C6H5. This gives us two important clues. One is it's an electrophilic addition reaction, and second is that the chlorine's electronegativity value is higher than that of iodine. Because of the electronegativity difference, the bond in ICl is polarized, carrying a delta positive charge on the iodine and delta negative charge on the chlorine. In the addition reaction, the alkene group will add both the halogens, but chloride ion, being more electronegative, will latch on to the stable carbocation, which is the one which is the most substituted carbon atom here. So this one. Hence the chlorine will get attached here and the iodine will get attached here. So that's what we have to show in the mechanism. So drawing the structural formula, we have C6H5, the phenyl group here, CH double bond C, CHO, and then we have the methyl group here, and here ICl is close by with a delta positive charge on the iodine and a delta negative on the chloride. The curly arrow always goes from the electron dense area to the electron deficient area or the positive charge, and then what happens to this bond is now it breaks, transferring both the electrons to this chloride ion, which becomes a heterolytic fission. Now let's draw the next part. C6H5 CH, this becomes a single bond here now, carbon, CHO and CH3, and let us attach the iodine atom here and put the positively charged on the carbon atom, and there is this chloride ion with the electrons here, and therefore we should show the curly arrow from this to the carbocation. The question is asking us to show the mechanism for formation of one of the products, and we are showing the mechanism for the major product. So this is the major product here, C6H5 CH, iodine here, and the chlorine here, and CH3. The question needs us to explain which of the two possible organic compounds is more likely to be formed. So you'll say here, this is the major product, as is attached to most stable cation, carbocation, which is the one with the most substituted one or the least hydrogen atoms. Fine. Question 21. This question is about aromatic carboxylic acids and their derivatives. The flow chart below shows some reactions of compound H. In the boxes, draw the organic products of these reactions. So let us look at compound H. It is phenol with a carboxylic acid group attached to it. This is otherwise very commonly known as salicylic acid. Right. Now let's look at the first reaction, Na2CO3 aqueous. We know that phenol is a weak acid, therefore it cannot react with Na2CO3, but the carboxylic acid group will react. Therefore, the resultant product will be, drawing the phenol here first because it's not going to react. And then we have C double bond O, and then this will become a salt here with the minus sign and with Na positive to be shown next to it. The next reaction with NaOH aqueous. It's a very strong base, and therefore both phenolic group as well as the carboxylic acid groups will react with NaOH. So to draw the product, so here we need to show O minus with Na positive as a salt next there, and then we have got C similarly O minus Na positive. We show the charge here clearly. Okay. Phenol can enter into an electrophilic substitution reaction with the bromine, and the phenol group is 2,4,6 directing. That means the bromine can get attached to any of these carbon atoms. Let us first of all draw the compound H. And we have the C double bond OH here. So bromine can get attached here or here or here. So since it didn't say any excess bromine or anything, we are just going to attach the one bromine atom here. Part B. Compound H is used in the synthesis of polymer I as shown in the flow chart below. Complete the flow chart by drawing the structure of the acyl chloride and 2 repeat units of the polymer I and stating the formula of the reagents required for the first stage on the dotted line. An acyl chloride is a derivative of the carboxylic acid group with the OH part replaced by chlorine. Now here we just need to replace OH here and put Cl here, and also look for which reagent will help do this. So whenever we want to convert the COH group into an acid chloride, we need to react it with thionyl chloride, which is THIONYL chloride. Thio means sulfur, it is SOCl2. Okay. This converts the COOH group to COCl. That's the note for us, not for actually writing in the actual exam. Okay, just for reminding you. So completing the structure here, C double bond O, just this OH is going to be replaced by the chlorine atom. Now we need to draw the 2 repeat units of polymer I. A polymer is obtained when one part of the molecule reacts with the other end of the molecule and forms multiple units of the same. So looking at this here, we can see one part is COCl, which is an acid group, and here OH, an alcoholic group. Therefore, the alcoholic and the acid group will react to form what? An ester link. So let's draw this ester link here. C double bond O, then O, and then draw one unit here. We have got C, and this part is the OH group of the carboxylic acid links with the hydrogen of the OH group, and that's how the link is formed. So now here the other end, and then put this. The question only asks you to draw 2 repeat units. That's fine. Question C. A cosmetic product containing 4 esters J, K, L and M is analyzed by gas chromatography and mass spectrometry. The results are shown below. Okay, next part of the question. The numbers by the peaks are the relative molar proportions of the compounds in the mixture. So mass spectrometry table is given where each ester and its MZ value is given. The concentration of ester K in the cosmetic product is 9.13 times 10 to the power of minus 2 grams per dm cubed. Using the results, calculate the concentration in moles per dm cubed of ester M in the cosmetic product. Give your answer to two significant figures. So the final ask in this question is calculate the concentration in moles per dm cubed of ester M. And what have we been given? The concentration of ester K in grams per dm cubed. And in the gas chromatogram given to us, the x-axis represents the retention time in minutes and the numbers by the peaks represent the relative molar proportions of each of the components in the mixture. So our strategy should be convert the concentration for K given in grams per dm cubed into moles per dm cubed, and then say that if that is represented by 4.3 in the gas chromatogram, then what would be the molar concentration for M, which is represented as 5.9, because they are all proportional and relative. So we could start by saying concentration of K in moles per dm cubed is equal to, we need to divide the mass by the MZ value to get the moles per dm cubed concentration. So we have mass is equal to 9.13 times 10 to the power of minus 2 and divided by its MZ value of 166, which is given in the question. Putting that into the calculator, we have 5.5 times 10 to the power of minus 4 moles per dm cubed. Okay. This is represented by a number of 4.3 molar proportion in the diagram. That is relative molar proportion. Therefore, concentration of M in moles per dm cubed will be equal to this thing, 5.5 times 10 to the power of minus 4 divided by 4.3 multiplied by the molar proportion of M is 5.9. So that is 5.9. Putting that into calculator, we get 7.56 times 10 to the power of minus 4 moles per dm cubed. Okay, putting that into two significant figures, 7.6 moles per dm cubed. Part 2. A general structure for esters J, L and M is shown below, where R is an alkyl group. Use the mass spectrometry results to deduce possible structures for esters J, L and M. So for some reason they do not want us to write the structure for ester K. I have captured here the names of the esters and the respective MZ value that's given earlier in the question. Now this is not a big challenge for us. What we could do is we calculate the MR value up to this part and then say that that plus R is equal to the MZ value of the whole ester, and from there we will maybe able to deduce the MR of R, and then from there we will be able to also identify what will be that alkyl group. So starting from the leftmost, 1 plus 16 plus 6 times 12 plus 4 times 1 plus 12 plus 16 plus 16 again plus R is equal to, putting them into the calculator and adding, we get 137 plus R. Therefore we could write R group in ester J is equal to 152 take away 137 which is equal to 15, and that translates to CH3. Okay, R in L is equal to, it was 180 minus 137 is equal to 43, and that will be CH3, that is 15, another CH2, another CH2. Okay, then R in M is equal, that's also 180, so minus 137 is equal to 43. So we need to rearrange this. Let's say a different arrangement. So the first alkyl group in J is CH3. Fine. So the second alkyl group is CH2, CH2, CH3. So creating some space. Okay, this is C, double bond O. Then we have got the ester link. Then we have CH2, CH2, CH3. For ester M, C, double bond O. Then we have to think about how we are going to arrange the same number of carbon atoms, 3, as well as the number of hydrogen atoms, 7, and how can we accommodate that? So it should be CH, CH3, CH3. There you go. Question 22. The relative molecular masses and boiling points of some fuels are shown in table 22.1. Write an equation for the incomplete combustion of heptane. Incomplete combustion means burning in limited supply of oxygen, and therefore the products will be carbon monoxide and water. So let's write heptane, that is C7H16 plus O2. We'll balance it later. We must give CO plus H2O. There are 7 carbons here, so this should be 7. There are 16 hydrogen atoms here. All of them should go to the H2O, so it should be 8 here, and then 7 plus 8 is 15, so I should put here 7.5 molecules of oxygen. Part B. Explain the difference in the boiling points of the fuels in table 22.1. One thing that jumps out of this from the table is pentane 1-ol, where the relative molecular mass is 88, but its boiling point is 138 degrees centigrade. So here we need to explain that pentane 1-ol can create hydrogen bonds between molecules because of the OH group, and hydrogen bonds are stronger than the London forces. Hence pentane 1-ol has the highest boiling point among the 3. Secondly, we also need to explain why there is a jump between hexane and heptane boiling points. So we could easily explain that by saying heptane has got a longer carbon chain, and this leads to greater contact between the molecules, resulting in greater London forces. This results in more energy being required to overcome these forces. So let's put them all in the as a trend here. Starting with the pentane 1-ol makes hydrogen bonds between molecules due to OH group. Hydrogen bonds are stronger than London forces and hence Penton 1-ol has the highest BP. Among the three compounds. Then we will talk about hexane and heptane. So we will say that heptane has a longer chain than hexane. How does this affect? This leads to greater contact. You can also say surface area contact or greater contact between the molecules resulting in greater London forces. This increases the BP as more energy is required to overcome these forces. So did we explain heptane has, hence heptane has greater or higher BP. Than hexane. Fine. Part C. Fuel additives are often used to improve the combustion of a fuel. Compound N is a fuel additive containing carbon, hydrogen and oxygen only. Complete combustion of 1.71 grams of compound N produces 2.97 grams of carbon dioxide and 1.62 grams of H2O. The relative molecular mass of compound N is 76. Calculate the molecular formula of N and suggest a possible structure for the compound. So we have a quantitative chemistry question here. At the start, let's write out a simple equation for the combustion of this compound. So the compound, let's name it as N itself, N plus oxygen, complete combustion, it gives CO2 plus water. Let's write out the other details that we know. 1.71 grams and its MR is 76. Then carbon dioxide, it's 2.97 grams and we know its MR is equal to 44, and water 1.62 grams, its MR is equal to 18. So the strategy for this question is, using the mass as well as the MR, we will find the number of moles, and using that we will balance this equation, and from the balanced stoichiometric equation we can find out the proportion of carbon, hydrogen and oxygen in the compound. So let's start by writing N CO2 and H2O in 3 columns. Okay, and let's write number of moles. Okay, so number of moles for N will be its mass over its MR. Okay, and then for CO2, 2.97 over 44 and 1.62 over 18. So using calculator we get 0.0225 for N. For carbon dioxide we get 0.0675, and then for water it is 0.09, so many moles. So now dividing by the smallest to find the proportion. So divide by 0.0225, we get this is 1, this is 3, and this is 4. So leaving out oxygen, the proportion by moles of the other reactants and products will be 1 N and 3 CO2 and 4 H2O. So the compound N must be, since all these 3 carbons are coming from N, so it must be having 3 carbon atoms. All these 8 hydrogen atoms are coming from N, therefore it should be having H8, but we are not sure about O. Let's put X here because some oxygen is coming from the atmosphere for the combustion. So going by the molecular mass, this is 76 is equal to 12 times 3, 36, plus 8 times 1, 8, plus 16x. Okay, from this we can easily figure out what is x. So 76 minus 36 is 40, 40 minus 8 is 32, 32 is equal to 16x, leading to x is equal to 2. Therefore oxygen is 2 in this compound. Therefore we can say N is C3H8O2, and then box it. Now we need to draw the structure of this compound. We have not been given any indication about the functional group in this compound, but knowing that mostly additives to fuels are usually alcohols, we can start writing an alcohol here, C, 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 and then hydrogen, hydrogen, so that makes 6 hydrogen, so we need 2 more. So we can say OH here and OH here, and that fits the bill. Part 2. Solcatol has been investigated as a potential fuel additive. Solcatol is synthesized from propane 1,2,3 triol and a carbonyl compound. Construct a balanced equation for this synthesis. Show structures for the organic compounds in your equation. Before we actually write out the final equation, let us investigate what should be the second reactant. We are told that it is a carbonyl compound, hence it should be bringing in the required number of carbon and oxygen atoms to make up the final product solcatol. Counting the number of carbon atoms here, we can see that there are 1, 2, 3, 4, 5, 6 carbons, and therefore since propane 1,2,3 triol has got 3 carbon atoms, this carbonyl compound also should have 3 carbon atoms. Now to deduce the number of oxygen atoms required in the second reactant, we should remember that it is a condensation reaction where one molecule of H2O will leave the reaction. Hence, triol has 3 oxygen atoms. Okay, the carbonyl compound has at least 1 oxygen atom, and that will make 4 of them. And then if I account for 1 water containing 1 oxygen going off, it will be minus 1, 3. And here I can see 1, 2, 3 oxygen atoms are there. Hence, the carbonyl compound has got 3 carbon atoms and 1 oxygen atom, and therefore it must be propanol. So starting with propane. Okay. 1,2,3 triol means one OH group here, one OH here, and one OH here. Okay. So this is going to react with the carbonyl compound, which is propanone. Let's write it in this fashion so that it will be easy for us to analyze what happens. In this reaction, what happens is both these hydrogen atoms from the 1,2,3 triol react with this oxygen to move as a water molecule. So let's write one water molecule here. The remaining part will be easy to draw now. So we got the OH group here, and then we have one oxygen here, and the remaining part of the carbonyl. So this is propane 1,2,3 triol. It's otherwise called glycerol, and this is propanone, and this is solketol. A scientist is researching compounds that might be suitable as fuel additives. One of the compounds gives the analytical results below. Elemental analysis by mass: carbon 54.54%, hydrogen 9.10%, oxygen 36.36%. And the mass spectrum molecular ion peak at MZ is 132. And then the NMR spectrum chart is also given. The numbers by the peaks are relative peak areas. When the spectrum is run without D2O, there are two additional peaks with the same relative peak areas at 11 ppm and 3.6 ppm. This is an important information for us. Okay. Use the information provided to suggest a structure for the compound. Show all your reasoning. So the main task for us is to find the structure of the compound. To find the structure of the compound, we have to find the molecular formula. Using the percentage composition given here, we can find the empirical formula, and using the molecular mass given here, we can finally find the molecular formula. So let's find the empirical formula. Let's put three columns here: carbon, hydrogen, oxygen. Then let's write percentage composition by mass. Carbon is 54.54%, hydrogen was 9.10%, and oxygen 36.36%. Then dividing by respective MR, we get for carbon 4.545, for hydrogen 9.10, and for oxygen 2.2725. Dividing by the smallest value here to find the ratio, we get carbon is 2, hydrogen is 4, and oxygen is 1. Therefore, empirical formula equals C2H4O1. Hence, empirical formula mass is equal to 24, 28 plus 16, 44. We also know that the MR of the compound from the MZ value is equal to 132, which is 3 times the EFM. Therefore, molecular formula is C6H12O3. Next part of the analysis is the proton NMR spectrum analysis to identify the structure of the compound. So let's write proton NMR analysis. The best way to do this is to document all the peaks and the chemical shifts relating to them. First and foremost, we see 3 peaks here, but don't forget there were 2 more peaks which were observed when the spectrum was analyzed without D2O. In presence of D2O, the OH gets depressed or suppressed, and therefore the 2 peaks which are seen without D2O must be because of OH. Anyways, let's document one by one the chemical peaks and the chemical shifts relating to them. So the first one is something like, it's like less than 1.5, so around 1.3, and this is around 1.4. So let me write this as 1.33 ppm, 1.4 ppm, and then this is 4 ppm, and we have got 2 more which were there when it was not done in D2O, that is 11 ppm and 3.6 ppm. Fine. Now let's write against 1.3 ppm what are the particulars there. So you can see that there are 2 splits. So it has got 2 splits. What does that mean? So next to one hydrogen atom, okay, and its area is 3 there, therefore 3, which means it has three atoms, 3 H atoms in the environment. The next one is 1.4 ppm. Looking at that, we can see it is singlet. Okay, so let's write it's having no split, singlet, therefore no hydrogen atoms adjacent. And then the area is 6, which means there are 6 hydrogen atoms in it. So 6 hydrogen atoms in the environment. Cool. Now 4 ppm, looking at that, we can see it's a quartet. So it is quartet, that means adjacent to three hydrogen atoms, and area is equal to 1, so it has got 1 hydrogen atom there. Now for each of these chemical shifts we need to identify the relevant groups. So 1.33 ppm, we will write the structure below that. 1.4 ppm, and then 4 ppm, and then 11 ppm, and finally 3.6 ppm. So the 1.3 ppm chemical shift represents 3 hydrogen atoms in the environment and next to 1 hydrogen atom. So referring to the data sheet, both 1.33 and 1.4 ppm have RCH groups. So let us write CH3 CH. Okay, that is this one. and for 1.4 ppm we saw that there were 6 hydrogen atoms and next to 0 hydrogen atoms. So it is CH3, CH3, and then to complete the 4 bonds. The 4 ppm chemical shift represents 1 hydrogen atom and adjacent to 3 hydrogen atoms. So for a chemical shift of 4 ppm, these are the groups possible. But knowing the molecular formula, we know that there is no bromine or chlorine atom in the compound. Therefore, it should be represented by CHO here. So it has 1 hydrogen atom is next to 3 hydrogen atoms, and it has got 1 oxygen atom as well. So let us try writing CH1 hydrogen atom, CH3 here, something here, but oxygen here. Now the functional group represented by the chemical shift of 11 is COOH. So let's write that here, COOH. Since we know that the D2O solvent suppresses OH, this must be OH. Now we can suggest a structure for the compound with the analysis we have done. The key aspects to be noted here are: 1. The structure should agree with the molecular formula we identified. 2. The groups in the structure should be consistent with the splitting pattern and the area of the peaks. As long as these are complied with, there could be other possible structures also, so don't worry. So the molecular formula is C6H12O3. Another thing to be noted here is our structure should have 5 hydrogen environments, because there are 5 peaks. Okay, now let us start writing out the structure. First and foremost, this carboxylic acid group will always be at the end of the structure, so it's quite safe to write this out here. And then this 1.4 ppm told us that there are 6 hydrogen atoms with no adjacent hydrogen atom in the next carbon atom. Therefore, since COOH does not have any direct hydrogen here, let's stick this CCH3 here, so that will satisfy that condition. Next, let us put this 1.3 ppm piece here, so CH3. What's remaining is the OH group, so let us attach it here. Now let us review our structure. First, the molecular formula: 1, 2, 3, 4, 5, 6 carbon atoms, that's fine. Then 3, 4, 5 plus 6, 11 plus 1, 12 hydrogen atoms, that's also fine. 1, 2, 3 oxygen atoms, fantastic. Now let us count the hydrogen environments. So this one is unique, so this is 1. This hydrogen is also unique, so it is 2. This is the third unique one. This and this will be similar, therefore they both will be representing the 4th one, and this is the 5th one. So 5 hydrogen environments is also satisfied. Now let us look at the chemical shifts and the splitting patterns. So this is 1.33 ppm hydrogen environment. So it has got 3 hydrogen atoms on it next to 1 hydrogen, so that is satisfied. Let's remove these numbers because they are confusing. They were just marking off the hydrogen environments. Okay. This single hydrogen atom adjacent to 3 hydrogen atoms is 4 ppm. This OH group is 3.6 ppm. This CH3 with 6 hydrogen atoms and next to 0 hydrogen atom is 1.4 ppm, this and this, and finally the COOH group is 11 ppm. All done, everything satisfied. Okay, so always please check these three aspects when you conclude your structure, whether the molecular formula is satisfied, whether the number of the hydrogen environments is okay as per the structure, and then go back and check whether the splitting pattern is satisfying what's given in the question in the chart. Well, that's the end of the question paper. Hope you enjoyed the walkthrough and found it useful. If you have any comments or questions, please feel free to post in the comment section in the video and I shall happily respond to it. Until the next walkthrough, bye.